Because I don't need to wait.
Okay, guys, here we go. So I gave you a handout just because some of this stuff is kind of tedious to write. But don't zone out on me, okay? That's the trade-off sometimes. Is if I give you notes that are already handwritten, sometimes you go off into another place. Okay, so stay with me here. So let's think about this. The integral from a to b of f of x, that means what? What does that represent? Area under the curve, right? Area under this curve, or the net area between this curve and the x-axis from x equals a to x equals b, right? Okay. Requires that a and b be finite. With me on that? I mean, they're always just hard numbers, okay? Finite numbers. And that f of x be continuous. Everybody's aware of that, right? In order to use fundamental theorem, we've got to have a and b have got to be finite, and f of x has to be continuous. If we come across integrals where these conditions do not hold, we use a different integration technique. And these integrals are called improper integrals. Okay? So there is, I mean, you can be asked to, in theory, find the area between a curve and the x-axis as x is approaching infinity, right? So like, how close is my curve going to get to the x-axis? Can I cut it off somewhere and find the area? Okay, so that's kind of the thing that we're talking about. So consider the following integrals that have infinite limits of integration. All right, so take a look at that first one there. It says the integral from 1 to infinity of 1 over x dx. Well, 1 over x is one of your parent functions that you talk a lot about in pre-cal. What's it look like? That, right? Okay. And at 1, 1, I would be, somewhere in here, right? And as x is getting bigger, the y value of the curve is getting smaller, right? So in theory, this is what I'm looking for, right? That area between the curve and the x-axis. Everybody with me?
Yes.
Okay. Well, what's the first issue that you see?
There's an infinity.
B is not finite, right? B is not finite. So the first thing that we're going to have to do is rewrite this integral so that I have, so that I don't have infinity as a limit of integration. So I'm going to do that by writing the limit as b goes toward infinity of the integral from 1 to b of 1 over x dx. And now I'm going to use what, do you think? Yes, I'm just going to find the antiderivative of it, right? I'm going to integrate. Okay, I'm going to integrate. So I'm going to have limit as b goes to infinity. What do you get when you integrate 1 over x? Oh, good, ln x. You are in there. Okay, ln x from 1 to b. Which is the limit as b goes toward infinity of what? Ln b minus ln 1. If I substitute infinity in for that b right there, what's this thing going toward? Infinity, right? It's pretty slow moving, but but it's increasing without bound. Minus, what's ln 1? 0. So, is there a finite area that I can find between this curve and the x-axis from 1 to infinity? No. even though that curve gets closer and closer and closer and closer to the x-axis, it will always continue to grow just fast enough that I cannot find a finite area. So what we say is the integral diverges. And that's going to be an important word for us in chapter 9. Okay, the integral diverges since the area continues to grow without bound. Okay, you good? All right, go to the next problem. Integral from 1 to infinity of 1 over x squared. What's 1 over x squared look like from 1 to infinity? Same kind of thing, but it approaches the x-axis faster, right? It approaches it faster, so now again the question becomes, does it approach the x-axis quick enough that I can find an area? Okay, that I can find it so that I can calculate a finite area. Your guess?
No.
Okay, let's see. All right, so what's my first issue?
There's infinity.
I have an infinite limit of integration which I cannot have. So what am I going to do? Limit as b approaches infinity of the integral from 1 to b of 1 over x squared dx. Which becomes the limit as b goes to infinity. What do you get when you integrate x to the negative 2?
Negative 1 over x to the third.
Okay, you guys can't answer me quickly enough, correctly enough, so you're going to have to start rewriting this. This is x to the negative 2, right? So I add 1 to the exponent, which is x to the negative 1, and I divide by it, right? So the answer to that is negative 1 over x. Okay, we got to be good at that. Don't be afraid to write it out. I would rather you write it out than call out random wrong answers. Okay, take the time to write it out. And this is from 1 to b, right? So I've got limit as b approaches infinity of negative 1 over b minus negative 1 over 1. Does it approach it fast enough? Yeah. The limit as b goes to infinity, this term's going to do what? Go to 0. Plus 1 is 1. So that's sort of interesting, right? 1 over x didn't approach the x-axis fast enough, but 1 over x squared does. Would 1 over x cubed?
Yes.
Yeah, why would 1 over x cubed?
Faster.
Because the denominator is growing faster than 1 over x squared, right? Okay, that's also going to be important for chapter 10. We're going to learn something called a comparison test. And so we have to understand how growth rates relate to one another. By the way, if any of you need a drink at some point because you're falling out, feel free, walk across the hall, grab a sip of water, and head back. I know you're tired. Everybody's tired. I'll bring it tomorrow for Valentine's. Does that work? Yes.
How come negative 1 over b was...
Because as b goes toward infinity, yeah, the bottom's growing infinitely.
Whatever.
Okay. Okay, are we good?
Yes.
So far, so good. All right, so take a look at the third example. Uh-oh.
And then 2 infinity.
2 infinities, right? All right, any idea on that curve? What the heck does that look like? I don't know what that curve looks like. Let's take a look. Let's see. Just out of curiosity, so we have a visual of what's happening. So I have e to the x divided by 1 plus e to the 2x.
Is it kind of like
Let's see. Oh, wow.
like I said,
Okay, I'll zoom in one more time. Huh. Okay, so I'm zoomed way in right now, right? But you saw the progression in the pictures. So clearly, again, the question is, how quickly are the end behaviors of the graph approaching your x-axis? Okay, so let's see. We have a picture at least of what we're trying to find. So my first issue again is what?
You got
2. So what do you think?
2 times 0 to infinity.
Can you separate it from negative infinity to 0 and 0 to...
That's exactly what I want to do. Derek recommends splitting it, going negative infinity to 0 and then 0 to infinity. Good split. Okay, good starting point. Okay, next issue.
You got to change your infinities to variables.
These, right? I can't have those. They're not allowed. What do you want to call this one? A. Good choice. I like it. So the limit as a approaches negative infinity of a to 0 of e to the x over 1 plus e to the 2x dx plus limit as b goes to infinity, e to the x, 1 plus e to the 2x dx. Oops.
Can we just do one limit where it's negative a in the first one and a in the second?
No, because they're not the same thing. No, don't do that. Now, you can skip this step. You don't have to have that step right there. It's just a good starting point to start thinking about it. All right, what now? Antiderivative, right? Antiderivative. All right, so I got candy for the first person that can come up with it.
You'll see.
Yell it out when you think you got it.
E to the x divided by negative 2.
Way to try that.
Oh, it would be negative 2.
Because we're not doing
One half ln of e of 1 plus e to the 2x.
No. Good try.
E to the x over x plus e to the 2x over 2?
No. Thanks for trying. I need it.
No.
Thank you for trying. I really do need it. No U substitution is required.
Wait. Is it inverse? Is it inverse too?
Wait, do we have to simplify?
Too good.
Listen. You've been on today, Derek. Sorry, it's stuck in my finger.
What was the other?
Inverse tan, e to the x. So limit a goes to negative infinity. Inverse tan
True.
e to the x from a to 0 plus limit b goes to infinity. Inverse tan e to the x 0 to b. Nice job, Derek. Limit a goes to negative infinity. Inverse tan e to the 0 minus inverse tan e to the a plus limit b goes to infinity. Inverse tan e to the b minus inverse tan e to the 0. So e to the 0 is what? 1. So where is tangent 1? Pi fourths. Minus e to the negative infinity. What's that?
Just
Basically, it's 0, right? It's 0. So where is tangent 0?
At 0.
0, right? At 0? Everybody with me on that? Because e to the negative infinity is the same as 1 over e to the positive infinity. E to the positive infinity grows without bound. 1 divided by something infinitely large goes to 0. And then where's tangent 0? 0. Okay. All right. So now this one. E to the infinity is infinity, right? So where is tangent approaching infinity? At pi halves. Very good. Minus. This one is where is tangent 1 again? Pi fourths. So what's your final answer? Pi halves. Who knew? So going back to the picture again. The area between that curve and the x-axis from negative infinity to infinity is pi halves.
Isn't there a way to find the area on the curve and calculate?
Yes, we've been doing that.
No, like not that, but like on the graph. I mean, like it shades it.
Sure, we did that.
No, like it shades it. Like
Yeah, I know. We did that. That's what I'm saying, Richa. We did that. We can go second calc 7, and we can go from, I have no idea what that is. I'll go negative 1 to 1. I hit the wrong thing, so. Ah.
oh my gosh. Yay.
We did that though.
Really?
Yeah. You're just forgetting.
You shaded it in?
Yeah, it's the very first way I taught you on the calculator.
Oh.
But it's good that it's good that you asked that, and it's good that it came back. Okay. All right, everybody good? So that's the first type of improper integral. Stand up and stretch if you need to, because there's a second type of improper integral that we have to go through. Okay? I'm trying to get us through so that we can have tomorrow to look at AP tests and stuff. Can you hang? Can you stay with me?
Yes.
Okay. I mean, I can stop right now, but then we're not going to have tomorrow to look at tests and stuff.
Don't
You want to stop it?
No, I'm good, thank you.
Oh, by the way, the chocolate you left me yesterday, was like chili pop rocks in there. Yeah.
I don't know.
The jury's still out on me for that. I don't know.
See what you gotta do.
Okay, so here's the second type of improper integral. Thank you for it. The first type of improper integral was what?
One of the integration.
Where your limits of integration were infinity or negative infinity. Oh, actually here, sorry, these are the rules for that. This is what we just did, if you turn the page. Integrals that have infinite limits of integration. This is the first type of improper integral. And what I did was summarize for you what we just did. If f is continuous on the closed interval or from a to infinity, then this integral gets rewritten like that. That's exactly what we did. If f is continuous from negative infinity to b, then we take this integral, we rewrite it like this. Yeah, sorry. I wasn't seeing it for some reason. By the way, you don't have to use A's and B's. You can use any letter you want. It's just what I use because it's in what we have in the fundamental theorem, so it makes sense. And then here's an example like what we just did. If we go negative infinity to infinity, you can split it up. We happened to split ours at 0. It made sense because in looking at the graph, it was symmetric about 0. But c could be any real number. You could split it wherever you want to. In the first two cases, the improper integral converges if the limit exists. Again, we're preparing for chapter 9 here. Okay, the words converge and diverge. If we approach an area, okay, a finite area, then we say that integral converges. So it converges if the limit exists, otherwise it diverges. It will continue to grow without bound. In the third case, if either integral on the right diverges, then the whole thing diverges. Okay, so are you with me? So like on the example that we just did, had one piece of this, had one side of it gone toward infinity or negative infinity, the whole thing diverges. So if you were doing this and on the first half you got infinity, you don't have to worry about evaluating the second half. Okay, yes?
Whenever we started that one, I asked if we could just do from 0 to infinity times 2 if it was symmetric. If it was symmetrical on both sides.
Mm-hmm.
Does the AP exam accept that, or do we have to do 0 to negative infinity to 0?
You could do it that way. Doesn't matter if you knew it was symmetric. Yes?
So what would happen if you did get, like, and if it was infinity?
Uh-huh.
What would you be?
You just stop and you put diverges.
Okay, that's it.
You don't have to put infinity, negative infinity, nothing. The actual answer is diverges. Okay? All right. Any other questions on that summary page? Nope.
So, which one of these examples converges?
Any of the ones where we got finite limits. So that one converged. This one converged to 1. This one converged to pi halves. All right. What time is it? Okay, here we go. So now we want to talk about improper integrals with infinite discontinuities. Okay, so in the first set of problems, we looked at integrals where limits of integration were either infinity or negative infinity. Now what we want to do is we want to take a look at integrals where there is a number within the interval that will give you, that will create something that's undefined. Let me start by just showing you the example. Okay, so take a look at this example right here. The integral from 0 to 1 of 1 over the cube root of x. What's the issue there?
Yeah, 0 is undefined.
The lower limit of integration, which is 0, makes that problem undefined. Okay, it makes that integrand undefined. So that's the other type of improper integral, is the type where your limits of integration themselves or a number within the limits of integration will create a function that's undefined, like the second example that I have here. Take a look at that one. This is the integral from negative 1 to 2 of 1 over x cubed. What's the issue there?
At 0.
At 0, that function is undefined, and 0 lies within
Negative 1
the-
to 2.
your limits of integration. So that's the second type of improper integral, and you have to be aware of that, right? I mean, because if you just take a look at that thing, you might just go ahead and do regular old integration and go from 2 to negative 1 without taking into consideration that 0, okay? So, anytime that happens, I'm going to do something similar to the problems that we just did. I'm going to have to rewrite them as a limit. So that's what all of this says. And I think it's easier to probably look at with an actual example. But in this particular problem, B made this function be undefined. So we have to do a limit as C approaches B from the left. And again, I'll make this make sense with the numerical ones, okay? But this is an overview of what it look like. So let's go here. And you've already told me that 0 makes this function undefined. We write this. And I'm going to use A and B again, just because A and B have always been my... Now, I have to decide what side to make this come from. Why the positive side?
It's the 1 to, because it's 0 to 1.
Because it's 0 to 1. Very good. Okay, because the interval is from 0 to 1. So I'm going to do the limit as A approaches 0 from the right. Yes, sir?
So, to determine whether it's right or left, you figure out whether you're going, like if that was negative 1 to 0, then it would be, you go from the left.
Correct.
Okay.
So you just have to figure out which, it's the interval that's going to tell you which side to come at on the value that makes it undefined. Okay?
Wait,
Yes,
so-
Ryan?
If the function were negative 1 to 1, what
Yes.
side would it come from?
You'd have to do it on both. The next example does that.
Okay.
Okay? Yes.
Okay, so it's not because it's 0 to 1 or 0 to 2, it's because it's on the positive side of 0.
It's because you're going from 0 to 1, right? You're going from 0 and you're increasing that value. So you would be on the positive side. Like 0 itself makes it undefined, but I'm supposed to find the area between this curve and the x-axis from 0 to 1. So this 0 right here, I'm going to end up right next to 0, but not 0 exactly, and I'll be on the positive side of it because 1 is also to the right of it. Okay? Did you have a question?
Would it give you the correct answer if you did it in terms of y and treated it like the ones we just did?
I've never thought of it that way. I would have to think. I'll need some time to process that. Okay. All right. So here we go. This is really x to the negative 1/3, correct? So when I integrate that, hang on just a second, Trey.
Okay.
When I integrate that, what am I going to get?
3 halves x to 2.
Good. I'm going to get x to the 2/3 times 3/2 from a to 1. And I have got limit as a approaches 0 from the right of 3/2, right? Minus 3/2 a to the 2/3. Which becomes what? 3/2. It's 3/2 minus 0. And really, this particular problem, it really is about notation, right? I mean, you're going up to 0. I can't include 0 because it makes the original undefined, but I'm finding the area from 0 to 1. Yes?
What happens if you just accidentally include 0? Are you just gonna get a wrong area?
No. I mean, in this one, it works out fine. You know what I mean? Like, in this one, you're going to get the same answer. If this is on a free response portion of the test, though, you're not going to get credit for your limits of integration because you've done something that you can't do.
No matter what, we'll always get the same area. It's just more about writing it the same way. Or for the most part.
Yeah, I think though where you can run into trouble, and I can't remember if we come across this in the next example or not. No, in the next one it works out fine. Some of it will, like it can put you on one side of 0 versus the other side of 0, so it can impact positive or negative. I'd have to find an exact problem where that comes into play. But that's what I was just saying, was that a lot of times it really is just about notation. Okay. Here, let's take a look at this next one and then we're done. Okay, so you already told me that 0 makes this thing undefined. So, if you want, you could start it like this. You could put in this step if you want. Or you could go directly to the next step. Okay, that's up to you. On my next step, what do I write for this one?
C approaches
-1 to 8.
I would say as B because it's the upper limit, right? And I'm approaching 0 from the left of 1 over x cubed dx. Is everybody good on why I decided from the left?
Do you still have to integrate that?
Okay. Yep, sorry. Okay, and then plus, and then what about the next one? The limit as a approaches 0 from the right of the integral from a to 2 of 1 over x cubed dx. So limit b approaches 0 from the left. That's really x to the -3, which when I integrate it is x to the -2 divided by -2, which is -1 over 2x squared, right? I'll let you keep going. What's this thing gonna do? diverge? Why is it gonna diverge?
Because you have a 0 in the, no.
One over time.
That right there, right? This is going toward negative infinity.
Is there something you can do so you don't have to write your limits every time?
You can write assume limits are there. Rotate.
Just a little simple.
What time is it?
Let x equal the answer.
It's going too slow. It's going slow.
AP's gonna be like. Geez, not right.
It's 20 points.
Plus
You're
5
at that. You're not.
Correct answer.
for the correct answer. Plus 1 for the correct answer minus 19 for no work.
I'm finished. I'm just gonna.
All right, let's do 1 through 5 on the worksheet for homework. But I've got a little, I want you to do a couple out of the book as well.
Enthusiasm. I go home and like have fun while I'm done. So I was used to that.
Page 467. So the improper worksheet here, 1 through 5. And then page 467 in your text.
Minus.
Nine through 19 odd. These problems right here, look at me, people. These problems right here, the 467. And all of these are by hand. There's no calculator involved, okay? These problems in here, you're going to see partial fractions. You're going to see integration by parts. You're going to see substitution, all of which you have not had to do in a while because we've been punching buttons, okay?
Are we gonna see
So,
yours?
very important for you to practice these. I haven't taken up a homework assignment in a while. You never know.
So are you giving us our practice test?
Yes. And then one other thing, not that you guys have time, but I will as a bonus, and I don't give bonus very often. This back page, the back, I told you to do 1 through 5 here. If you do 6 through 10 and bring that to me, I'll count that as extra credit. You can see from my paper that this is not an easy task. Okay, I'm just giving you a heads up, so don't kill yourself, okay? I don't know what I'll do with it.
Wait, can I see the grade I got on part A?
Thank you for your attention. I'm sorry I've been talking so much. I'm trying to get out of that mode and put you back into other mode, regular mode.
Can I see my test grade?
Have a great day.